Assalamualaikum and good morning. Today, we would like to continue our discussion on turbulent boundary layer, and I would like to introduce you another method called the empirical form. So again, by this calculation, we could get the drag coefficient, or CD, and also we could calculate the value of delta, which is the boundary layer thickness, and also we could calculate the drag force from the value of CD that we get from the previous calculation. So this is another method that you could use instead of using the 1/7 power law. So actually both has their own advantage, and sometimes the empirical form will give you more accurate answer. So the empirical method of predicting turbulent flow quantities on a flat plate with zero pressure gradient is based entirely on data. It is more accurate than the power law, but also more complicated. So the time average turbulent velocity profile can be divided into two regions, the inner region and also the outer region. So the velocity profile for inner region is defined as U over U tau equal F. Equal F here means equal the function of U tau, Y, and nu. So nu here is the kinematic viscosity. Okay, so what is U and what is U tau? So let's say we have a velocity profile, a flat plate here. So and then we have the velocity profile here. So the U here is actually the velocity for each location of Y, and the U tau here is actually we refer to the velocity that gives certain value of shear stress. But you know the higher shear stress is actually at the region near the surface here. So the velocity at this region is actually influenced by the shear stress. So we calculate the ratio between the velocity and also the velocity that influenced by the shear stress. So and then the equation for U tau here is equal to tau naught over rho square root as shown in this equation. So and then we have another region which called the outer region here. So the equation for this velocity is U infinity, capital U, minus U bar over U tau is equal to the function of Y over delta. So U infinity here is actually the free stream velocity. The free stream velocity means the incoming velocity, and the U bar here is actually the average velocity at certain height or at certain region. And U tau here is actually the velocity if affected by the shear stress. So in this idea, the scientists who calculate like this one believe that in certain range of Reynolds number, the turbulent velocity is actually will occur like this one. So it will increase at certain region, and then it will a little bit decrease, and then it will go like this one. Okay, because they want to calculate the effect of this increment. So they start to calculate, they start to divide into the inner region. So it's something like here, and then the outer region that start from here to the along the flow. So because of this one, we need to get calculate the effect of the buffer zone here. Okay, so it is okay. We are not going to calculate this one because this is numerical. So mean we need to calculate like Blasius. We need to substitute all the coordinates and we get all the value and so on. So but I just want to give you an idea of this one. And then from this calculation, first we could get the value of local drag coefficient. So local drag coefficient means that, for example, if we have a flat plate here, so we have a boundary layer. So at one specific point here, we could calculate the effect of shear stress. So we reflect the effect of shear stress as the local screen friction. So we write down as CD with the small d as the subscript. So the equation is 0.455 over ln 0.06 Reynolds number square. So I hope you could remember this equation. And then you know that from this value, we could calculate the total drag coefficient. So by the idea of, we have the force here. So it is equal to tau times A. Okay, and then for the tau here, so actually we could calculate by using the CF 1 over 2 rho A, rho U square. Okay, however, for this one, for the tau here, so we need to integrate it. Okay, we need to integrate them. So, and then we could get the value of CD. So I hope you could see our previous notes to how to integrate the value of tau here, shear stress, and then we could get the value of drag force. So, and then after we doing that, we could assume that the total drag coefficient CD with the capital D here is equal to 0.523 over ln 0.06 Reynolds number square. Okay, so I hope you could remember this equation, and this equation is very good because it can be used until Reynolds number equal to 10 by the power of 9, and it only has error around 2% only. So however, when the Reynolds number become larger and larger, so the error is around 4%, but I think it is quite good. The error is quite small for our consideration. And finally, for this equation, so we could assume that we could calculate the value of boundary layer thickness delta by using this equation. So it is U over U tau equal 2.44 ln U tau delta over nu plus 7.4. So the idea is we could get the value of delta here, but we need to calculate the value of U tau at early of our calculation. So here the value of nu here is the kinematic viscosity. So please be careful. Do not assume this is as the velocity of V. So this is the nu, the kinematic viscosity. So let's say we see the example. For example, example 1 here. Estimate the boundary layer thickness at the end of 4.5 meters long flat plate if wind flow on it at 3 meters per second. Also calculate the drag force on one side if the plate is 3 meters wide. Use the empirical data, assume that the temperature is 20 degrees Celsius. So we know that the temperature is 20 degrees Celsius, so maybe we need to calculate based on this value. Okay. So the boundary layer thickness can be calculated by using this equation. So this is the equation that I showed you previously. So however, we need to calculate the value of U tau first before we could proceed in this equation. So we know that the U tau here is equal tau naught over rho, and then we need to calculate the value of tau naught here by using this equation. So which is tau naught, it is CD times 1 over 2 rho U square. And CD here is the local friction coefficient. And the local friction coefficient is given by this equation. So, and then first, we calculate the value of Reynolds number. So the equation of Reynolds number is rho Ux over mu. And it also can be written as Ux over nu. So if you want to use mu here, So mu is the dynamic viscosity and nu is the kinematic viscosity. You could get the value of dynamic and kinematic viscosity from this table for 20 degrees Celsius. So we substitute everything, and x here is the length of the plate. So it is given by the question here, 4.5 meters long. So we substitute everything, so we get it is around 8.9 times 10 by the power of 6. So and then we assume that it can be used the empirical, because the limit is still can be used until 10 by the power of 10 actually. So and then we calculate the ln 0.06 Reynolds number. So we calculate as this one. Please make sure that you multiply the 0.06 with the value of Reynolds number, and then you get the value of ln, and you get it is around 13.1926. So we substitute the value here in the CD. So this is the local C small d, the local drag coefficient. And then it will calculate that the value of tau naught is equal 1.416 Pascal. We substitute to this equation to get the value of U tau. So, and then it is equal to 1.084 meter per second. And then we substitute in this equation, we could calculate the value of delta here is equal to 0.05567 meters. And the drag force can be calculated by using this equation, because we know the value of CD here. So the CD is 0.523 over ln 0.06 Reynolds number square. We substitute the value and we get it is around 0.003. So, and then we could calculate the drag force by using this equation. So we substitute the value of CD as 0.003, and finally we could get the drag force that occur on that flat plate. It is around 21.94 Newton. See example 2. Estimate the maximum boundary layer thickness and the drag due to friction on the side of a ship that measures 40 meters long with a submerged depth of 8 meters, assuming the side of the ship is approximated to a flat plate. The ship traveled at 10 meters per second. Use the empirical method and compare with the result using the power law model. So in this question, they ask us to imagine that, for example, we have a ship like this. So, and then the water here is, the depth is 8 meters. So this is 8 meters, and the length of this one is around 40 meters. So we assume that now we need to calculate the boundary layers for this area only, and we assume it is suited with the flat plate. So why it's mentioned like this one? Because for the flat plate here, so the pressure gradient will always equal to 0. So mean it is a zero pressure gradient condition. But as we discussed in the transition in chapter 5, so if we have a curved surface like this one, we maybe have some effect called the separation. So we assume that we don't make any deal with the separation. So we assume that for sure the body of ship here is curved at certain degree. So we assume that it is okay for us to assume that the plate here is actually flat like this one. So, and then in this question, we need to compare with the empirical method and with the power law model. And the power law model here is referred to 1/7. Okay, but sometimes you need to use the power law if the question gives, okay, please calculate the drag force if U over U here is equal to Y over delta by the power of 1/9. So means that you need to calculate everything. You may see the reference of the calculation, but you need to use the Y over delta by the power of 1/9. So if the question just say the power model, so it is okay for you to refer as 1/7 because this is the most common equation for the turbulent model. So we take properties of water at 5 degrees Celsius, because at 5 degrees Celsius, around 4 or 5 degrees Celsius, the density of water is 1000 kilogram per meter cube. Okay, now we start with the calculation of tau naught. So this is the equation. So this is the value of CD, the local drag coefficient, and we could calculate the tau naught. It is equal 82.80 Pascal. So, and then we could calculate the value of U tau. So it is the square root of tau naught over rho, and we get it is around 0.288 meter per second. So we substitute in this equation. So, and then we could calculate the value of boundary layer thickness is 0.384 meter. So, and then we could calculate the drag force by using this equation. FD is equal CD times 1 over 2 rho AU square. And before that, we need to calculate the value of CD, and the value of CD according to the empirical method is can be calculated by using this equation. So, and then we substitute all the values, so we get it is around 0.001904, and then we could get it is equal to 30,464 newtons. Okay, so that is the answer that we calculated using the empirical method. And now we calculate the calculation by using the power law, by use the power law method. So first, we need to estimate the Reynolds number. So the Reynolds number can be calculated by Ux over nu, or rho Ux over mu. So nu here is the kinematic viscosity. So we substitute everything. So we get it is around 2.6 times 10 by the power of 8. So, and then to make it more specific, so let's say we use the velocity profile of y over delta by the power of 1 over 9. So because it is ranged from 10 by the power of 8 to 10 by the power of 9 here. So we take it as y over delta by the power of 1 over 9. So and then please bear in mind that for turbulent boundary layer, we cannot use the idea of Newton viscosity of law. So mean the tau is equal mu du dy is cannot be used here. But why? Because if we use this equation, when we substitute the value of y equal to 0, we get everything is equal to 0. So our mathematical calculation is correct, but this situation is not reflected the original condition. It is not about the mathematics calculation. It is about to choose the right equation for the right situation. So we will take the value of shear stress according to the Blasius calculation. So it is normally it will give in a question. So let's say for n equal to 9, so the value of tau is given like this one, 0.023. So sometimes it will give you nu over u delta, or sometimes it will give you mu over rho u delta. So this is, you must alert that mu is actually equal to rho and nu. So which is the mu here is the dynamic viscosity, and nu here is the kinematic viscosity. Okay, so and then we start with the von Karman. So we know that von Karman is tau rho u square d theta dx. We substitute the value of theta that we have. So here you need to calculate it by using the equation of integral of 0 to delta u over u times 1 u over u dy. So this is the theta, the momentum thickness. So I hope you could do this. Substitute the value of u over u with y over delta by the power of 1 over 9 here. Okay, and then you will get it is around 9 over 110 theta. And then we substitute in this equation, and then we equating these two shear stress. So these two shear stress mean you substitute the value of this one with the value that we get from the Blasius calculation. So and then when you equating that equation, yeah, I hope you could solve it, because I already give the example in previous lesson. So we could get the delta is equal 0.433x over Reynolds number by the power of 1 over 5. So and then it is equal to 0.358 meters. So if we compare from both methods, we found that the empirical method will give 0.384 meters, but the power law method will give 0.358 meters. So if we compare this value, we found that result from the power law method is a little bit lower, and the difference is about 6.77%. So might be in terms of boundary layer thickness, it can be accepted by this one, because the difference is not so big, because okay, now we see about the drag force. So and the drag force is FD is equal to CD 1 over 2 rho AU square, and we need to calculate the CD. Okay, from the velocity profile, I hope you could calculate the CD. Okay, please refer to the previous lesson. I already give you example for 1 over 7. Okay, so let's say we calculate that, we get the value of CD is 0.071 over Reynolds number by the power of 1 over 5. And then we have 1 over 2 rho AU square. So we substitute everything here. So and then we get it is around 23,511 newtons. So and then if we compare this one, so for the empirical method it is 30,000 newtons, and but from the power law is 23,000 newtons. So and then from this calculation we found that the power law methods will give a little bit lower. Okay, so but the difference is big, it is around 22%. So for calculation for drag force is quite important, because it will give us the condition of that ship, the power net need to be installed for that ship to make sure that it could cruise with enough power, because the drag force here is actually the resistance that fell by the ship. So I hope you have idea about these two equations. So normally it is easy. So for this one, so it's look easy to get the to calculate the empirical calculation, because all the data is given. So however, in reality, you need to make sure that you get the proper data before you substitute with the equation. Next, I would like to introduce you another calculation for boundary layers, but we need to calculate the laminar and turbulent at the same time for a boundary layer. So previously in our calculation, when we talk about Blasius, for example, or we talk about the another velocity profile like u over u is equal to uy over delta plus y over delta square. So it is actually, we assume that it is for fully laminar. So means we assume that all the boundary layer is laminar, and then we go for the u over u, the 1/7 power law. U over u is equal to 1 over delta by the power 1 over 7, or we use the empirical calculation and empirical methods. So and then this is our assumption is our boundary layer is fully turbulent. Okay. However, okay, so you need to understand this, because if our object, the distance of our plate is short and the velocity is very, very slow, so maybe our boundary layer is fully laminar. And then if our plate is bigger and the flow is higher, so we have the fully turbulent. Okay, so however, sometimes we have problem, because maybe we have a condition where the lamina is almost half of the plate, for example, and then it has transition, and then it's turbulent. So means that the existence of laminar boundary layer here is cannot be ignored. Okay, we will discuss about this in this lesson. Okay, so let's say this is what I said previously in the next slide, because sometimes the existence of laminar boundary layer here is quite dominant. It might be 1/3 of the plate or bigger than that portion. So if this one means that we need to calculate, we cannot assume the it is improper for us to assume that the boundary layer is 100% laminar, because if it's 100% laminar, it means that the boundary layer thickness that we get at the end of this one is totally different with the turbulent. So, and then again, so we cannot assume that it is 100% turbulent, because if we assume it is 100% turbulent, maybe we calculate the boundary layer thickness here is a little bit higher compared with the actual condition. Yeah. So the effect of the boundary layer thickness is actually it will increase the value of drag force, means that we get a wrong value for the drag resistance. Okay, so what we need to do is, okay, so because we already know all the methods to solve the laminar boundary layers and also the turbulent boundary layers. So we discussed about this topic by using an example. So for example, estimate the boundary layer thickness at the end of 4-meter long flat plate surface if the air-free stream velocity is 5 meter per second, and predict the drag force if the surface is 5-meter wide. So we assume that we have 4-meter long and 5-meter wide here. So this is 4 meter, and we have the wide here is 5 meter. Okay, so neglect the laminar boundary layer, and also we need to calculate the Renault critical. So Renault critical here is the changes from laminar to turbulent. So let's say we take the Renault critical is 5 times 10 by the power of 5. So we need to take account the laminar boundary layers. Okay, so because to make this calculation simpler, okay, so we could simplify it is we could take the Blasius exact solution as our representative for the laminar boundary layer, and the 1/7 power law, mean y over delta by the power of 1/7, as our representative for the turbulent boundary layer. So means that all the equation is given, is calculated in the previous lesson. So I hope you could get the value to solve these problems. Okay, let's say we go for the first condition. So we neglect the laminar boundary layer. So let's say we calculate the Renault number at the edge of plate. So this is the equation of Renault number, rho ux over mu. We substitute all the value. So we get that it is 1.25 times 10 by the power of 6. So it's quite a little bit, it's large. So we compare with the critical Renault number, means the borderline between laminar and turbulent boundary layer. So we take as 5 times 10 by the power of 5. So we found that 1.25 times 10 by the power of 6 is fully turbulent now. So means we have right to say that it is okay not to calculate the laminar boundary layer, because the flow is actually bigger, the Renault number is increased, is over the limit of a laminar boundary layer. So now we assume it is fully turbulent boundary layer. So according to the 1/7 power law, we could calculate the boundary layer thickness. So delta is 0.38x over Renault number by the power of 1/5. So we get it is around 0.0917 meter. So, and then we could calculate the drag force by using this equation. So this is everything is calculated previously by using dy over delta by the power of 1/7. So we get it is around 1.28 Newton. Okay, so it's straightforward. Later on, we will compare our calculation. So let's say we need to take laminar boundary layer into our calculation. So first, we need to calculate the boundary layer thickness delta for the laminar boundary layer only. So what we need to do is we do, for example, we have a plate here. We assume that the flow will create laminar boundary layer. Later on, the transition at very short period occur, and then the turbulent boundary layer occur. So, so the limit for the laminar boundary layer is called the Reynolds critical. So the Reynolds critical here in this situation is taken as 5 times 10 by the power of 5. So means that because we know the value of Reynolds number here, means that we could predict the length of this x exists. So we could calculate by using this idea. We do some reverse calculation. Let's say the Reynolds number is 5 times 10 by the power of 5, and the Reynolds equation is rho u x over mu. So we could substitute everything, then we could calculate the value of x is equal to 1.5 meter. So 1.5 meter means from the zero here. So laminar boundary layer will occur until 1.5 meter. Then from this point, the turbulent boundary layer will occur. So the value of 1.6 here will give us, if we compare 1.6 meter that have a laminar boundary layer with the total length is 4 meter, we could find that laminar boundary layer is actually covered around 40% from the whole plate. So we found that it is too large. It's not small area. It's a large portion of plates covered by the laminar boundary layer. So it means we cannot neglect the calculation of laminar boundary layer. So first step means that you need to determine whether the laminar boundary layer can need to be accounted or not. Normally, if the laminar boundary layer is more than 10%, so I suggest you to include the calculation of laminar boundary layers. Okay. So if less than 10%, for example, your laminar boundary layers only around 5% for the total length, so it is okay for you to assume that all the uh, boundary layers occur on that object is fully turbulent. So, and then we need to determine the thickness of the boundary layer at the end of the laminar boundary layer. So why? So it's referred to this one. So we have a plate here. So and then we have a laminar boundary layer, and then it's changed to the turbulent. So first we need to calculate what is the thickness of this one. So this is a delta. Because this is the laminar boundary layer, so we need to use the equation for laminar boundary layer. So according to the Blasius equation, the delta is equal to 5x over square root Reynolds. So we could calculate it is equal to 0.0113 meters. So means that this delta is equal to 0.0113 meter. So and then, okay, so from this, what actually our purpose of this calculation is, okay, so we refer to this figure first. Okay, so now we could calculate the thickness of this one. Okay, and the purpose of this calculation is actually we need to calculate the value of x prime. So x prime is now after this point, the boundary layer will change into the turbulent boundary layer. So maybe it can be draw like this one. And you must know that this is not the starting point for the turbulent boundary layer, because we assume that all our calculation is actually based from the x0 and y0, where the delta is also 0. I mean, we start at 0, 0 at this point. Whether it is laminar or it is turbulent, our calculation, our derivation of equation is actually based on this situation. But at this point, we found that the x is not equal to 0, and the delta here is also not equal to 0. The delta here is actually 0.01186. So it is equal that the amount that we calculated by using the idea of laminar boundary layer. So this is the laminar boundary layer. So it will create this thickness. Okay, what we need to do is we need to interpolate. Okay, we need to interpolate this line until we could get its real starting point. So at this point, so the value, we could assume that the x will, for turbulent boundary layer only, the x here can be assumed as 0, and then the y is 0, and also the delta is 0 at this point. So we need to calculate, we need to find what is the real starting point for the turbulent boundary layer. So that's what we need to calculate now. So let's say from the Blasius calculation, we get the boundary layer thickness is 0.0113, and then this value is actually also the answer for the turbulent boundary layer thickness at critical point. So I draw it again here. So we have a laminar, and then we have turbulent here. So this turbulent is not, this is not the real starting point for the turbulent. So the turbulent should be start here, for example. So but this thickness is actually shared. So the turbulent boundary layer also give the laminar the boundary layer thickness at this point, and the laminar boundary layer also give the same thickness at this point. So according to the laminar calculation here, so we found that the thickness here is 0.0113 meter. So, and then we could use this value to predict the distance of this one. Okay, so from the 1/7 power law, the delta here, the equation is 0.38 x over Reynolds number by the power of 1 over 5. We substitute the value of delta here with 0.0113 meter. So we could get the value of x is equal 0.292 meters. So here again, so we have an x here. At the same time, the Reynolds number here is equal to rho u x over mu. So please be careful that this x is also need to be calculated. So means that first you need to expand the value of Reynolds number here, then you could get the value of x is equal to 0.292 meters. So means that this 0.292 meter means this is the distance from here. So from the boundary layer to the real starting point of the turbulent boundary layer. So means that the distance here is 2.92 meters. Okay, so we could calculate the real x-axis for the turbulent boundary layer. So the real x-axis means that the turbulent boundary layer is actually start at this one. So means that for our calculation for turbulent is actually need to be start here, mean we need to assume that the 0, 0, the origin for the turbulent boundary layer is start here and end at this point. Okay, previously we know that the distance of laminar boundary layer here is 1.6 meters. But this 1.6 meters is actually not the real starting point for the turbulent boundary layer. It is the critical location, means the changes from the laminar to turbulent boundary layers. It occur at 1.6 meters, the distance of x, but not the real starting point for the turbulent boundary layers. So to calculate the real starting point of the turbulent, so we show as x turbulent here. So x turbulent here is the length of the flat plate, means the total length of this one. The total length of this one. So, and then we minus the transition. So the transition is this one, means the length that we calculated by using the laminar boundary layer. so which is 1.6 meter, and then we need to add again with the value of x prime. Okay, so and then we could calculate this one. So it's the distance of the x for turbulent boundary layers is 4 minus 1.6 and plus 0.292, so it is equal to 2.69 meters. It is mean that to calculate the turbulent boundary layer by using turbulent boundary layer calculation method, we only need to consider plate length of 2.69 meter only. So it is because in laminar or turbulent theoretical, we develop their equation by assuming boundary layer starts at x equal to 0 and delta is also equal to 0. So, and then we could continue our calculation. So, for example, we know that the x turbulent, so is 2.69 in the turbulent boundary layer thickness. We could find the answer of Reynolds number, rho u x over mu. So we substitute the value, we could get the Reynolds is 8.4 times 10 by the power of 5. So we substitute in this one, so we get the delta is 0.0668 meter. So this value is more accurate compared to the first calculation. If laminar boundary layer is neglected, the boundary layer thickness at the end of the plate is 0.0917 meters, compared with 0.0668 meter here. So it is 37% higher compared to the second calculation. Okay, now we go for the calculation for the drag force. To calculate the drag force, we cannot use drag force equation for turbulent boundary layer alone. So you know the reason, because in this situation, they are both effective. Okay, we must use specific value of drag coefficient. So it's because the laminar boundary layer was influenced the formation of the total boundary layer. In this case, we use CD as shown below. So in this calculation, we need to use the idea of this one. So for example, we calculate the Reynolds number for the total length of plate. So it is 1.25 times 10 by the power of 6. So and then we need to use the specific drag coefficient as stated here. So later on, I will explain. So for example, we use CD equals 0.073 over Reynolds number by the power of 1 over 5 minus 1,700 over Reynolds. So why we need to deduct a little bit? Because the laminar boundary layer influence the total resistance. So this is the value of the drag force from the total turbulent, but we need to deduct a little bit. We need to minus with certain coefficient, because the laminar boundary layer influence the formation of boundary layer. So we substitute everything, so we get the CD is 0.00304. So we use the value of CD in this equation, so finally we could get the drag force is 0.885 Newton. So how to choose the value of CD if we have laminar and turbulence boundary layer in one situation. So normally it based on the critical critical Reynolds number. So if the critical Reynolds number is 5 times 10 by the power of 5, so we take this value. So if the critical is increased into 6 times 10 by the power of 5, so then we could have this one. Okay, so this is okay. So actually, if the critical Reynolds number is increased, so we need to change a value at these terms actually, and this term is actually not calculated by using mathematical. So it's but it is actually depends on the experimental value. So it is some kind of a curve fitting. So we have the experimental data, and then we continue, we try to plot a graph, and then we normalize, we simplify the equation of the graph, and then we could come out with this one. So that's why if you see the first idea here is actually the same amount, because it is actually the amount, the CD comes from the calculation of the turbulent boundary layer. So we need to deduct it a little bit, because the laminar boundary layer will reduce the resistance that occur on that object.